Good morning students, welcome you all on YourPedia. Today we are going to discuss some of the important previous year problems of NIC. Okay. So if we move on the first problem, with the help of this problem you get an idea that how easy problems are coming NIC. So you have to prepare according to previous year problems. If we talk about first problem, the smallest element that can be found in binary max heap. Suppose we have a max heap that is 100, 90, 80, 60, 10, 20 and 30. Now what is the problem statement? I have to find the smallest element in max heap. How much time it will take? If in a binary max heap I want to find the maximum element, we know that maximum element always present on root node. Getting my point? But what about minimum element? If we talk about the maximum element in a heap, then maximum element in max heap is always present at the root node, but minimum element keep in mind, minimum element always present at the leaf node. Fine. So to get the minimum element from the max heap, what is your approach? The first approach is you can delete first maximum element, then delete second maximum element, then delete third minimum element. The last element in my heap is the smallest element in max heap. But what is the time complexity? To delete an element it take log n time. So I have to delete n minus 1 element because nth element is the smallest element in max heap. So I need to delete n minus 1 element from max heap. But what is the problem with that? This is not the optimal answer. So it gives me order of n log n, and as you can see that order of n log n is the A option. Okay. So don't try to hit the first option. Now, so what is the second approach? If we talk about the second approach, you can say like this. We can know that the almost n by 2 element of the tree are present, almost n by 2 element of the tree are always present at leaf node. Are you getting my point? Fine. So can I do a search for in the array having n by 2th index to nth index or n minus 1 index? Fine. So if I have an array of n element, if I want to find the minimum element, how much time it will take? Order of n. But in this case I start my searching from n by 2th index till nth index. Getting my point? So how much time it will take? I have to perform n by 2 comparison at max. So what is time complexity? N by 2, which means order of n. So my correct answer is order of n for this problem, not n log n. Are you getting my point? So you have to find out the optimal answer. Keep in mind. If we go for problem next problem, that is problem 2, worst case time complexity for all the operations. We have to find the worst case time complexity in binary search tree. As we already know, what is the property of binary search tree? At left hand side less than equal to element are present, and at the right hand side maximum, or I can say at left hand side the elements are less than equal to the root, and at the right hand side elements are greater than equal to the root. But what happened? We are talking about worst case time complexity. Can I say it is a binary search tree? Yes, it is a binary search tree because every time the right child is the maximum or equal to its parent node. Getting my point? In the worst case, what is the height of my binary search tree? The height of binary search tree is order of n. Are you getting my point? So if I want to insert, first of all, if I want to search any element, suppose I want to search 40. So I have to start from the root, then 20, then 30 and then 40. So how many comparison I have done? Order of n. Next, if I want to update, I want to make this 40 as 50. Again, I have to start with 10, 20, 30. First of all, I need to find out where is 40, then update that value. Updation required order of 1 time, but searching or reach out to that element requires order of n time. So again, order of n time. If we talk about delete operation, I want to delete 40. First of all, I have to reach to element 40. Again, it will take order of n time. So the correct answer is order of n. Next, there's number of queues needed to implement stack. As we already know, to implement stack, we required 2 queues. Getting my point? So total number of queues required to implement stack is 2, and again if I want to implement queue using stack, also we require 2 stack. Fine. So the answer for this problem is 2. Next, Dijkstra algorithm is based on greedy approach because always we find the local minima. Getting my point? In the Dijkstra algorithm, that is single source shortest path, we use greedy approach, that means always find the local minima. Next, in which type of following data structure an element is inserted at one end, that is called rear, and delete at the other end, that is called front. Getting my point? So what is that data structure? Queue. Stack is called first in last out. Fine. But queue, in queue data structure, that is first in first out. Getting my point? So the correct answer is queue. So these are the 5 basic problems. You can find out that the complexity of these problems are very easy if you attend the or you can, if you can go all the basis of these problems. If you have any doubt, you can reach out to NIC module of YourPedia. Fine. And if you have any doubt, please comment in the video section. Okay. Thank you so much.